Hello and welcome to our fifth and hopefully final video in the Unit 12 Solubility series. We're going to be talking some more interesting details about solutions, starting where we picking up where we left off in the last video. We'll be starting this time talking about saturated versus unsaturated versus supersaturated. I kind of mentioned this in the last video. A saturated solution means that the solution has the maximum amount of solute dissolved in that solvent at that specific temperature, meaning no matter how much more I put in there, no more will dissolve. It is holding as much dissolved solute as it can. If you add any more, basically it's going to sink to the bottom. Now that doesn't mean that nothing's happening, it just means that it's hit that point where the solute that's dissolving is happening at the same rate as the solvent or the solute that is crystallizing back out. Okay, so it looks as though nothing's happening. In reality, there's no net gain or loss of dissolved solute. It stays the same, although there's still, of course, something going on. It's just at an equilibrium. If you have a solution that's unsaturated, that means that you can dissolve more solute in it. If I take water and put in a pinch of salt, well, it dissolves that salt into a saltwater solution, but it's unsaturated because there's a lot more salt I can dissolve in it before it hits that saturation point, before it hits that max amount dissolved. Like I said, there's still more room for more solute. Now, a supersaturated solution, this is interesting, and I'll talk about some common supersaturated solutions that you run into in nature. It looks like I have a blue mustache. If you take a solution that's already saturated and you heat it up, you increase the temperature, well, then it reaches a new point and you can dissolve more solute in it. Well, let's say you dissolve more solute in that hot solution, then you let it cool back down, and something funny happens. What happens is that more solute stays dissolved than would normally be possible, and we say at that point that that solution is supersaturated. Some examples of supersaturated solutions in nature. Honey is a supersaturated sugar solution made by bees. They dissolve all this stuff in there and then they dehydrate it by heating it up with their bodies and getting rid of that extra moisture. It concentrates it down into a very, very thick, very supersaturated sugar solution. If you physically disturb a supersaturated solution, meaning that you bump it just wrong or you drop in one more crystal of solute, then what will happen is that all of that overly dissolved solute will start to recrystallize and start to come out of solution. I've got some chemical hand warmers I may have shown you in class that work on this principle. Whenever you physically disturb them, the crystals, which have been supersaturated, I believe it's sodium acetate, they've been supersaturated, they start coming out of solution, which causes it to get very hard, very cloudy, and it causes it to release quite a bit of heat energy. And that's something we'll mention too in just a minute. Anytime you have dissolution or crystallization, there's an energy change that accompanies that. So here we see in one picture various types of solution. Over here we have an unsaturated solution. You can dissolve more solute in it than is currently dissolved. We have a saturated solution where it has taken on as much solute as it can. You can see here there's some solid solute starting to collect at the bottom of this tube because the solvent can't hold anymore. Now I take that and I heat it up. Well, I can dissolve even more in there, but then if I cool it back down and I disturb it, then it will start to grow crystals very, very rapidly. And you can see that as I go from unsaturated to saturated and supersaturated, my concentration increases. Concentration, you may remember from class, is just an expression of how much solute is dissolved in a given amount of solvent. We'll be looking more at concentration here in a minute. Whenever you've got solute and solvent interacting with each other, a good rule of thumb that dictates whether something will or will not dissolve is this one here: like dissolves like. What this means has largely to do with whether or not your substances, if they both happen to be nonpolar, then a nonpolar solute will dissolve in a nonpolar solvent. And nonpolar, again, meaning substances where you don't have strong charges on it. Polar solutes will dissolve in polar solvents because, again, those charges allow them to have something to grab onto. However, if you try and mix the two, then you will not get dissolution. Polar solvents will not dissolve nonpolar solutes, and vice versa. Ionic compounds tend to dissolve in polar solvents, but nonpolar molecules or nonpolar solvents don't work well with them. Water, you of course know, is a very ionic, a very polar substance, and so a solution where something is being dissolved by water is very, very common. It's got its own name. It's called hydration. If I take salt and I hit it with water to dissolve it, I can also say that I'm hydrating that salt. A lot of substances, whenever they recrystallize, they will capture some of those water molecules inside the crystals, and that's what's called a hydrate. If you remember, we've done a couple labs with copper 2 sulfate. Those are those really pretty blue crystals. The ones you're looking at that are that real pretty blue are what are called pentahydrates, meaning that for each copper 2 sulfate unit, there's 5 molecules of water locked in there. When you heat those up, then the water leaves the crystal and becomes more of a pale white or very pale blue substance. If you add water back into it, it takes on that nice deep blue color again. Interesting substance, talking back about soap, which, if you recall from our video on water, is a surfactant. Soap allows substances that are polar and substances that are nonpolar to dissolve each other. What we have right here is we have water, we have soap molecules. Here's a soap molecule, this is sodium stearate, and that sodium stearate is stuck into a big blob of oil or a big blob of grease. Now when that happens, that soap, which has both polar and nonpolar parts, allows water to wash away that oil, which is how soap or detergents work. Okay? It allows water, which is polar, to dissolve nonpolar substances. It's kind of a go-between. Okay? Whenever you've got solutions being made or being crystallized, there's always heat energy going on. Now this will go back to what we talked about back in thermochemistry, talking about whether a change is endothermic or exothermic. There's always an energy change going on. If energy is absorbed, of course, remember that's endothermic. Okay, endo, into. Hey, it's time to go home. Made you jump. Or made you wake up. I've been talking a long time here. I know it's time to go home. It may not be a huge amount. It may be a very small amount. If that energy is given off, of course, that's what's called an exothermic change, where the energy is being released. It's exiting the system. Typically, the amount of energy that's either released or absorbed is referred to as a substance's heat of solution. Some substances, you put them in water and they dissolve, they take in energy and it feels cold. Some other substances, you put them in water, they get hot, they release energy, it feels warm to you. And again, remember, we're talking about enthalpy, we're talking about delta H. If delta H is positive, heat's absorbed, it's endothermic. If delta H is negative, then the heat gets released. It's an exothermic change. It gets hot to the touch. There are different ways to describe concentration of solutions. One, you can just say percent by mass. You see this a lot in consumer products. They won't have like a molar or a molal concentration. They'll say such and such percent alcohol or such and such percent pain reliever in this cream. Okay? Percent by volume is another one. Rubbing alcohol is one that you see. Rubbing alcohol, I think you can buy over the counter in two different concentrations. One is like 80 some percent alcohol, and the other is like 90 some percent alcohol, and that's by volume. Parts per million, parts per billion. You see this in your water reports that the city has to send out every year, telling you, okay, for this contaminant, lead or aluminum or rat poop or whatever, they say it's got this many parts per million or this many parts per billion, meaning that out of a million quantities of water, 1 or 2 or however many parts are this substance and everything else is just water. Now, molarity is the one that we use most often in chemistry class. When we've talked about that, symbolized by a big M. It's also called molar concentration. We'll look at that some more here in just a moment. There's another one that some chemists use called molality. It's symbolized by a lowercase m. We're not going to use that quite so often. Molarity is defined as moles of solute per liter of solution. Molality is moles of solutes per gram of solvent. It's just a little bit different way of looking at things. Talking more about molarity, here again is the formula. Molar concentration, big M, equal to moles of solute divided by liters of solution. You give the units for this in moles per liter. We have done, or we will do, some practice in class on calculating with this. Fairly easy calculations, 1 or 2 steps, not a big deal. In practical terms, if I've got, this is what's called a 1 molar solution of something, that means that it has 1 mole of solute dissolved for every liter of solution. It doesn't mean I've got a whole liter of solution, but it means that if I had that concentration, if I had a liter of it, then it would have, a mole of dissolved solute in there. Whenever you go to make these solutions, it's always a good idea to start by putting the solute in the bottle first and then adding the solvent, because if you put in the solvent first, if you get too much solvent, as you add that solute in there, it can actually overflow your mark that you're trying to hit, and then you have to start all over again. Okay, one more thing to talk about is what's called dilution. When I dilute something, I change its concentration. Dilution usually means that I am reducing how concentrated it is. But basically, to take a concentrated solution and then to dilute it. For instance, I showed you something in class where I took a concentrated tube of red dye in water and I diluted it by pouring a little into a new container and adding more water to it. And you could see it was less concentrated because it had a paler red color. The total moles of solute in there remain the same. What changes is the amount of solution. So as I increase the solution amount, I decrease the molar concentration because there's more solvent and the same amount of solute. Okay? And here's the formula for that. The molar concentration of your starting solution times the volume of your starting solution will equal the molar concentration of your new solution times the volume of your new solution. Okay? In other words, as this number, this V, this volume, if it goes up, then the molar concentration will go down in order to keep these two equal. So here's a problem for you. If I've got a 15.8 molar nitric acid solution, how much of that would be required to make 250 milliliters of a 6 molar solution? So I'm going to be diluting down to 6 molar solution. So that's, So this right here is what I'm shooting for, that many milliliters of that solution. So if I increase, I'm working backwards here, if I increase the solution from 6 molar to 15.8, then it should be a much smaller volume than 250 milliliters, or 0.25 liters. And let's take a look at this. Here's what I'm given. I'm given that molar concentration 1 is 15.8. I'm looking for volume 1. I'm looking for the volume that I'll need to start with. Molar concentration 2 is 6 molar. Volume 2 is 250 milliliters, or 0.25 liters. Here's where I'm going to work. I rewrite my formula. I plug in my numbers. Okay? Now in this case, you wouldn't necessarily have to change this into liters since all you're doing is a dilution. So I can leave this as milliliters if I want to. If I take 6 times 250, and then I take that number and divide by 15.8, the answer is going to be 95 milliliters of this first solution. So if I was going to do this in real life, I'd measure out 95 milliliters of this concentrated nitric acid. I would add water to it very carefully, because you never want to add water to acid. You'd probably more estimate the amount of water, add your acid to it slowly, and then very gradually dilute that with water until you got 250 milliliters, and that would give you 6 molar nitric acid. This brings us to the end of the video notes for this unit. Thanks for watching. I'll see you in class.